Yeah, so what Charles Darwin observed was the animals and the trees and everything on the island kept on changing so that it could stay alive longer. The birds had to change their diets. They couldn't eat worms anymore because there weren't any more worms. So they had to eat something else. They ate plants. They ate fish. The turtles that came on the island, they had to change their way of life because eventually, if you're on a deserted island, all the resources are going to disappear. New things are going to come up. So that's what he observed. So he observed a bunch of specific events, and he made a general statement from it. That's what the inductive reasoning is all about. You look at one or two things specifically, and you make a general statement from it. In education, I observe that students who study more than 10 hours for a test make A's. So what's my general statement going to be? If you study more than 10 hours, you'll make an A for a test. As opposed to deductive reasoning. Deductive reasoning is just the opposite of it. Is you take a general observation and you make a specific statement out of it. So one's going from specific to general, and the other one goes from general down to a specific. The inductive. I observe that students study 10 hours, made an A. Now the other one, deductive reasoning, I can say that if you study 10 hours, then you'll make an A. Will it always be true? No. That's why it's a general. That's why it's a general observation. Generally, if you study 10 hours for a test, you'll make A. Because there are some instances where you make a B. In other words, what the deductive reasoning is saying is that the amount of time studying will not guarantee you anything. It will be a better chance at getting that event. So, this is creating a specific statement from general observations. Now, in inductive reasoning, when we do an inductive reasoning, a statement from it, those are called conjectures, hypotheses, or educated guesses. You've heard hypothesis before. Have you ever heard of conjecture? A conjecture is just a statement that is not as solid as a hypothesis. Hypothesis can be tested. A conjecture is well, it's like when you watch a police show, you have an idea who the criminal is. That's your conjecture. With what you're given so far, you're saying that this person did it. That's a conjecture. Until more information is given and you can make a better decision on it. So basically it goes from educated guess to conjecture to hypothesis. That's the level of importance. Here's an example. The sum of any two-digit number will always be a 3-digit number. There's a statement. The sum, what does sum mean? Okay, so what operation do I use there? Addition. So the sum of any 2-digit number. What does digit mean? Actually, no. It refers to a number. Digit means finger. Because the Greeks, when they did that's why they did that. That's why they call it a digit, because how do we count when we're kids? With our fingers. So yeah, so digit, yes. We refer to them as numbers now, but digit actually means finger. So the sum of any 2-digit numbers, any two 2-digit numbers, will always give you a 3-digit number. Like 79 plus 41 equals what? Don't use a calculator, use a pencil and paper. Use your brain. 120. I don't want to see any calculators in here unless you start using pencil and paper and brains. So I have the sum of two 2-digit numbers equals a 3-digit number. $80 plus 90. $170. Okay, the sum of 2 digits. So is this a true statement that the sum of any 2-digit numbers will always give you a 3-digit number?
Involved.
Go ahead.
Was that in 79.50?
No, digits.
Okay.
Digits are digits. You can't have a 0.5 of a finger. How about 10 plus 11? These are 2-digit numbers. That equals, is that a 3-digit number? No. Is what's called a counter example. All I have to do is find one counterexample to prove that this statement is false. Why is it false? Because of this word right here. It says always gives you a 3-digit number. This is logic we're getting into. We have to, and reasoning. We have to understand what we have, what we're given, what we're looking for. So, whenever you're given a statement, first off, what you're saying here is this, the question I would ask is this a true statement? Is it true or false? It's false because of this one example. All you need is one example to prove something is not right that will ruin it for everybody else. All right. Strong versus weak. Inductive arguments. Okay, this is interesting also. I was on a side note. You notice how I use the word statements and arguments. Again, this is all has to do with mathematics, the concepts of mathematics. Because that's what these equations and stuff we're dealing with, that's what they're called. They're called statements. When you have multiples of them, they're called arguments. Whenever you're looking at true or false, if something's true or false, that's an argument. When each pair of statements, 2 or more statements together, will allow you to conclude an argument. So, what would be an example of a strong inductive argument. Yeah, if it's this thing here, it focuses every now and then. So an example of a strong inductive argument would be from the last U.S. Census, 42% of all males have college degrees in a science. Hey, you guys don't have to copy these, write this stuff down, because I'm gonna Xerox all these notes and send them to y'all. So you don't have to write word for word what I'm doing. It's just make sure you understand what I'm saying. Because I'm also going to send to you the video that corresponds with these notes. So you'll have the audio and the video. The weak inductive argument. My dad and brother don't fish, so I won't fish. Actually, or my dad and brother don't fish, so men don't fish. Let's stick with the men concept. This is a strong argument. This is a weak argument. It's more the information. It's the amount, the sample size. A census is what? What is it? Very good. Yeah, forget answer. What is a census? It's a count of the population, of the entire population. The U.S. Census is done every 10 years. Everybody in the United States should answer this questionnaire of all sorts of stuff, as education, income, all sorts of stuff. So that gives the government a much better picture of what's going on and where the money should go. So this is exact. If it says 42%, that means that's exactly 42% of the men have college degrees in science. That's a strong argument. So now I could say that if I have a room of 100 people, 42 of those people will have science degrees, at least. So I could be sure of that. Now, this one, the weak argument, my only information I have is my dad and my brother don't fish. So do all men follow what my dad and my brother do? No. Because that's not solid enough. Your next door neighbor, the person down the street, the person next state over. So the strength and weakness has to do with the amount of information you have to support your statement. Let's look at some more examples with reasoning. Numbers are 3, 12, 21, 30, 39. You should tell me two things. Is there a pattern? And the next number. There is a pattern? Or yes, there is a next number? Yes is not an answer. Is there a pattern? What is it? What's the pattern? Do what with 9? Yes. Well, we know from here to here if we add 9. From here to here if we add 9. From here to here we add 9. Here to here we add 9. So yes, it has a pattern. In mathematics, this is called an algebraic sequence or arithmetic sequence, meaning that all I have to do is add to get the next number. So the next number is going to be what? 48. Now, it's always going to be that easy? No. 3, 12, 48, 192, 768. You don't have to take pictures of everything. I'm going to make copies of this for you. Oh, move over. Move closer. Yes. Very good. This one times this equals 12. 12 times 4 is 48. 48 times, I thought it was going to take you longer than that. Good job. Your first couple of them, there you have inductive reasoning. If it works for the first couple, that's a specific observation, I can make a general statement. It'll work for all of them. So what's the next number going to be? 768 times 4. 8 times 4 is what? 32. 6 times 4 is 24, plus 3 is 27. 7 times 4 plus 2. Very good. Now you see what inductive reasoning, you induced the next possible conclusion. See this next one. Here's one.
Or in the same sequence.
Very good. That's exactly what it is. From here to here, you add 1. And then from here to here, you take this one and add another one. Here, you add another one, so it's 3. So this one, it's 1. This one is 2. This one is 3. This one is 4. This one is 5. This one's going to be 6, so the answer is 24. Yeah, very good. Let's see, I think I had one more here. Yes. We have another example. 3, 6, 18, 36, 108, and 216. Okay, so looking at that, what you said is, so this, to get to there, I multiply by 2, right? Then to get from here to here, I multiply by 3. Now, how about from here to here? Right. So there's a repeated pattern. The first one is multiplied by 2, then 3, then 2, then 3, then 2, then 3. So 216 times 3, 6 times 3 is 18. 3 plus 1 is 4. Very good. Very good. This is a very famous sequence of numbers. Which one? We'll do it again. I think you're right.
Yeah, you add 1 plus 1, and then you add 1, 2, 3, and you add.
Excellent. Very good. 1 plus 1 equals 2. 1 plus 2 equals 3. 2 plus 3 equals 5. 5 plus 3 equals 8. 5 plus 8 equals 13. 8 plus 13 is 21. So 13 plus 21 is? This is a Fibonacci sequence. This sequence helped develop a whole bunch of the complex theories of math. Chaos theory, how repeated patterns expand infinitely. So that's a very important one. Let's take another complex one that I thought was pretty interesting. 23, 54, 95, 146. This one, it'll look complex when you first. Yeah, it's getting bigger. 23, 54, 95. Then it drops back to 98. Get it? Yep.
31.
Yeah, yeah.
That's how you got to, you know what I mean?
Yeah, I said, here's soon there. So if you took the difference here and added 10 to it, and then added 10 to that. Good observation, but it stopped right there. I see what you're saying. It would have worked. The difference between these two is 31. 31 plus 10 is that from this one. 41 from that plus 10 is that. But no. Yes. It has to do with not looking at these as two. This is not 23. It's 2 and 3. 2 plus 3 is what? Add 1 to this number. 5 plus 4 is add 1 to this number. 9 plus 5 is add 1 to this number. 6 plus 4 plus 1 is 11. Add 1 to the last digit. So add all the digits to the number and add 1 to the last digit. 7 plus 1 plus 1. 9. Add 1 to the last digit. 9 plus 8 is 17. Add 1 to this one. So that's inductive reasoning. I like that. Is there only one way of doing these things? Is there only one way of... So if I gave you this sequence... Is there only one way of doing this? For finding the next number? You won't find it on me. You have to look at the board and work on your paper and see what you get. Yeah, we're still in inductive reasoning. Because we notice specific observations, we're going to try to make a general statement from it.
You asking what you're doing right here?
I'm asking you, how many ways can you do this? Are each of these solutions, are they unique? Or can you have more than one solution? No, not math. I'm saying in general, in reasoning. If I multiply 1 times 2, I get 2. 2 times 2 is 4. So how do I go? So I could multiply by 2. Like from here, forget this one. Now from here, if I add 2. So what's the next number going to be? If we did the add 2, it'll give us 6. If we do the multiply by 2, it'll give us 8. So the next number in a sequence, next event in a sequence may not be that easily determined. That's to come up here, we had a whole bunch of sequences first. We have to make sure the pattern is uniform. If it's a short list, then you have too many mistakes. If it's a short list, there's not enough information to make a long-term prognostication. A long-term, you can't be sure that the long-term event's going to be true forever. Okay, now those always work for numbers. How about this? What's the next picture going to look like? We have two things we can notice here. What's the next shape going to look like? And what's the next pattern going to look like? Because there's multiple moving parts here. It'll be a circle. And where's the one dot going to be? Right here? So the 1 will be here, the 2 will be here, and 3 will be here, right? No, because look at it. It starts here to the right. It goes up to the top. It goes to the left. It goes to the bottom. So it's going counterclockwise. So basically it's going to start over. So basically what's happening is you're going to repeat the sequence now. The next one in the sequence will be the first one again. So we know it's circle, square, circle, square. It has to be a circle. The dots are moving in a counterclockwise direction. This one. What's the next one going to look like? It'll be a square. Very good. It'll be two sticks. Right. Get it? Okay, so those are all examples of inductive reasoning. Is we see a specific observation and we're making a general statement. Because our general statement is we can tell you what the next one's going to be. Now let's look at deductive. Let me see. Getting a specific conclusion from general statements. So we have general statements, we come up with a specific conclusion. Find pictures of this one. I have to write this one down. Okay, here it is. Step 1. Select any number. Multiply it by 6. Add 8 to the product. Divide the sum by 2. Subtract 4. The quotient. Here's what the question is going to ask you to do. Form this with any two numbers. Derive a conjecture on what you see. So, with these 5 steps, do it to 2 numbers and tell me what you see, what you observe. Well, let's do it for 3 numbers, so we better see a pattern. Finish it. Just sit there, do the work. Know it? What's your conclusion? I say, pick 3 numbers, work these 5 steps, and tell me what you got. So you have to do these 5 steps 3 times with 3 different numbers. So first step, select any number, multiply it by 6, add 8, divide by 2, subtract 4. And tell me what your conjecture, and then let's prove it. So what's the first number y'all picked? Give me a number. Okay, let's do 3. 3 times 6 is plus 8 divided by 2 minus 4. So our answer is 9. Another number. Okay, yeah, let's just get some bigger numbers. So, times 6 plus 8. Oop, 74. Divided by 2. Subtract 4. Another number. 6. 6 times 6 is plus 8 divided by 2 minus 4. So what pattern do you see here? This whole process really, from here to here, what's really happening to the numbers? Times 3. Everyone, so no matter what number you give me, if I give you 20, what number is going to be here? 60. Because what it says is, whatever I start off with, if I times 3, I get this answer. Times 3, I get this answer. Zero times 6 is plus 8 divided by 2 minus 4. Yeah, so 0. Actually, it's a good point. Does it work for negative numbers? For negative numbers. Let's try negative 3. That's good. That's good observation. Let's see. So negative 3 times 6. plus 8. Yeah, in a couple of weeks, when we do the math, the actual math part, the number part, we'll go through all these rules. Divided by 2, minus 4, negative 3 times 3 is negative 9. So it may work for negatives, just not 0. Let's try negative 5. So what we're saying is we're predicting the number is going to be negative 15. Negative 5 times 6. Negative 30 plus 8. Negative 22. Negative 22 divided by 2. Negative 11 minus 4. So it does work. It's just you can't do 0. Very good. I'm glad you asked that. We can use positive and negative. When it says pick any number except 0. Let's talk about that really quick. We're using the term real numbers. What is a real number? The answer is going to surprise you. Any number that is not imaginary. That is a legitimate answer. Because there are two sets of numbers that we have in our numerical system. Real numbers and imaginary numbers. That's called a complex number. Equals real numbers plus complex numbers. Imaginaries. So we have two types of numbers that we deal with, real numbers and imaginary numbers. Imaginary numbers are just that, like square root of negative 1. Doesn't exist. Because what times what? What number times itself gives you a negative 1? There's nothing. So it works, it exists, but it doesn't exist. The real numbers consist of these real numbers. To begin with, our real number system begins with natural numbers. Natural numbers. If I ask you to start counting, where would you start? Yeah. So natural numbers are our counting numbers. If we take the natural numbers and add a 0 before them, those are called real numbers. Because it starts off with a whole. Okay, now that's just going this way. We can figure out now we have numbers this way. So a numeric system, we have positives, negatives, and zeros, is called the integers. We have another set of numbers. Because are all numbers in our number system, are they all just numbers? No, there's stuff between 1 and 2. There's an infinite number of numbers between there. Those are called rational numbers. Rational is just a fancy way of saying fractions. Every number is made up of a fraction. Three over 5. 2 is a fraction. It's 2 over 1. So every number is a rational number. In rational numbers, you can have repeating or terminating decimals, or non-repeating numbers. For example, the number 3 over 5. In decimals, it equals 0.6. It stops. It's only one decimal place. The number 1 over 3 is 0.3333 forever. If it goes on forever with the same pattern, what we do is put a bar over it. If you ever see a number with a bar over it, that means all the numbers after that are whatever that is. If I had 0.25 like this, your number would look like this forever. These are all symbols. This is all symbols that PEMDAS never even gets near touching. So that's why I don't like it. Rational numbers, decimal numbers, have here's a decimal. I can't use those. 7.452019568. No, that on the left-hand side. What place is that number? That's the ones. Very good. What place is this number? That's the tens. This number? Hundreds. And this number? Thousands. And again, 10,000s, 100,000s, millions, 10 millions. It always goes the ones, hundreds, 10. Or 1 tens, hundreds. So we have 1 million, 10 million, 100 million. 1 billion, 10 billion, 100 billion. 1 trillion, 10 trillion. It keeps on going from there in that pattern forever. Now, on the right-hand side, from the decimal, what's this number called? Okay, before they're called decimal numbers, right? Why are they called decimal numbers? What does deci mean? Means 10. Well, because we have, okay, they're called digits because we have fingers. We have how many fingers? 10. So that's why it's called decimals. Each digit represents a decimal. Each position of these things shows us a new location, all based on tens. Our number system is written this way. Here's a decimal. Ten to the 0 power. That's this first one. Then we have 10 to the first power. 10 to the second power. 10 to the third power, and so on and so forth. Okay, now what is the 10 to the power 2? What does that mean? Yeah, it means 10 times 10, which is what? 10 times 10 is a 100. It's the third space. The third space is called the hundreds. What is 10 to the first power? It's just 10. This is the tens location. Anything to the 0 power is 1. So this is the ones location. 10 cubed is 10 times 10 times 10, which is 10 with 3 zeros, which is the thousands. So the exponent gets bigger as we go to the left. When we go this way, we have negative exponents. And so on and so forth. What does 10 to the negative 1 look like? A negative exponent simply means flip it to the bottom. So 1 over 10 is 0.1, which is what that is. It's the tenths location. Over 10 is the tenths. This one, 10 to the negative 2 is 1 over 10 to the 2. 1 over hundredths. So this is the hundredths. It means 0.01. So each of these numbers have specific locations, and they have specific names for them. This is the tenths, hundredth. What do you think the next one's going to be? Thousandths. Thousandths. Then 10 thousandths, 100 thousandths, millionths. Everything to the right ends in THS. So now we talk about rounding. So if I say round to the nearest hundredths, what am I asking you to do? The hundredths. This is the tenths. This is the hundredths. Since I'm looking for the nearest hundredths, I'm looking at this number. So the rounding rule is this. Look at the next number to the right. This one. If we're rounding, Either this number is going to go up to 7 or stay at 6. That's what rounding is all about. I'm rounding to the hundredths. So, if the next number is between 5 and 9, then add 1 to the number. So if this number was a 5 to a 9, I would add 1 to this number. It is between 0 and 4, just drop it. So your number is 4.56. I rounded it to the hundredths. Round to the 10th. Round this number to the tenths. So here's a decimal. This is the tenths. So I look at the next number. Is it between 5 and 9? Yes. So I add 1 to this one. And there's my answer. That's the rounding rule. You okay with that? Bigger one up here. 7, 4, 7, 6, 2, 4, 2, 0, 5, 6. Round to the nearest $100 million. Million. $100,000. And tens. So take that number and do those rounding. It's push.
The one before that, 4.5, whatever it was.
Yes.
And you're at
Yes.
$5.
Yes, what that means is that you look at the dimes. If that number there is between, well, those things are different because they always say you want to round it up because they want to get the more money to the charity. But if it's truly rounding, if after a decimal, if that number is between 5 and 9, then this number jumps up to 5. If it's between 0 and 4, then it's just dropped, you just have a $4 bill. So that's the reason it's not too advantageous for businesses to do rounding to the nearest dollar. All right, so 100 million. How to make that longer? 100 million. Which digit is the 100 million's number? The 4. Yeah, because this is the 1, 10, 100, 1,000, 10,000, 100,000, million, 10 million, 100 million. So the first one is the 4. Since we're rounding to the 100 million, we look at the number before it. That's between 5 and 9, so what do we do with this number? We round it up, so it becomes 5, and the rest becomes zeros. So since I'm rounding to the 100 millions, everything else is going to be zeros. So the million is a 6. So I look at the number before it. It's a 2, so what do we do that? Just drop it. It becomes zeros. When you're dealing with the rounding, you have to go either, it's going to be, this number goes up or down, the rest are going to be zeros. $100,000s. The 100,000s is this one. So I look at before it. It's a 4, so what do I do with the numbers after it? Do I round this one up or leave it alone? Leave it alone. And put the rest zeros. Since I'm rounding to the 100,000s, the rest will be zeros. How about to the tens? Do I round up or leave it alone? Right, because the number before it is a 6. So I add 1 to that and make that a 0. So that's what I do. Use rounding. Give me an example when you would use rounding. There. Here's an example. You purchased bread for $2.59, detergent for $5.17, a sandwich for $3.65, an apple for 47 cents, and coffee for $8.79. The bill was $24.67. Is this a reasonable amount? Is this a reasonable bill? Let's round. Let's see what happens. $8.79. That's close to what number? 9. 47 cents is close to 50 cents. 365 is close to what? 517 is close to 5. 259 is close to 9 plus 5 plus 4 plus 3. So 5 plus 4 is 9. 9 plus 9 is plus 3. So this one says it should be about 21.50. Give or take, so it's not that bad. So it's reasonable. It's within the ballpark. If the bill was $42 and something cents, then we know something's wrong. This is what anytime you guys should go to the grocery store, check your numbers. Because there have been numerous reports of grocery stores not changing the numbers on the computer as fast as they change it on the shelf. So if it's a sale and it's not ringing up as a sale, guesstimate it. So you see what you have. So there's an example of why you would use rounding. There's another one. A carpenter works full-time. And earns $28 per hour. estimate the weekly salary, estimate annual salary. Remember, the optimum word is estimate. It doesn't have to be exact. It just has to be an estimate. Yeah, it's full time. Yeah. Yes. Remember, full-time work week is 40 hours per week. Estimate. I don't want. Yeah, I want you to just give me something in about 5 seconds to tell me how much he's going to make for both of these. So, if he's making $28, what do we round this number up to, or down to? 30. So, we have $30 per hour times 40-hour work week. 3 times 4 is 12 with 2 zeros. So he'll make roughly about $1,200 a week. What's his annual salary? Again, we have 30 hours. Annually, people work about 2,000 hours. That's how they ballpark estimate, because you have 2 weeks vacation anywhere you work. So you work 3 times 2 is 6. You have 4 zeros. So it makes about $60,000 a year. That's how you estimate what you have. But you have to also remember, we rounded up $2. So we can go further and say, okay, 2,000 times 2 is 4,000. So if we set 4,000, he makes more like 56,000. Minus taxes, he makes about 8,000. So that's how you use estimation. Any questions so far? Estimate using graphs. Next class hour, aren't we? What time does class start? 9:30? It goes 9:30 to 10:50, so we should be on break now. And I told you guys I'd never keep you that late. But
We're talking estimate. What's a factual of 28,000 hours? We're on a week, we'll get 5. That's only for the
that's if that's if you're looking for the exact estimate. We're estimating, yeah. So
estimate.
yeah. Okay. Okay. What graph is this called? Pie chart, yeah. Now, inside these, let's say this is 41%, this is 18%, this is 9%. It's not exact, but if you add up all these percents, what should they equal? They should equal 100. But I'm just saying, this is one chart that people use. Why do they use graphs and charts in business? Now, these are exact. Because if I'm a business, I want to know exactly all my customers. 41% of them use the computer between this hour and this hour, or use social media during the day. So this, when you see a chart on a report, it's accurate with all the data given. But the reason they use it in business is once they get this data compiled, you say, if we had 30,000 employees, how many use social media during the day? This is use social in day. So how do we find this number with this information? Remember, if we had 30,000 employees, I want to know, after this data set was collected, this is what we found out. So how many of our employees are using social media? I have 41% of what? Yeah. So we take 30,000, or as you said, 41% of 31,000. But how do we do that mathematically? %, of 30,000. Whenever you see the word "of" in a math statement, that means multiplication. Now, you can't multiply a percent. How do we convert percent to decimals? Percent means 1 over 100. So the symbol percent means 1 over 100. So it's 41 times 1 over 100. (41 over 100) times. I can get rid of 2 zeros. So I have 41 times 300. 41 times 3 with 2 zeros behind it. So 12,300 of our employees are on social media during work time. So that's how you use this chart. You know you have a specific number you're looking at, 30,000 employees, and you can now go through and calculate each one of those. Yeah, I because I can't pull it up on here. What kind of chart, what kind of graph is this? Very good. It's a bar chart, bar graph. Okay, this is in number of employees. These are the years. You have to have a legend. So what these bar charts tell us is we have the male and females each year, how many number of employees we have. Or anything, I mean, it can be anything. And on top of these things, you have a specific number that dictates on how much there actually is in there. 240. So say this one is 270 and 350. So these charts, this information, okay, first off, whenever you have these, whenever you have charts, time always goes on the x-axis. Whenever you do any type of charts, time is always, why is that? Why is time always on the x-axis? Well, no, you can't change time. Time always moves. The number of employees can change, but time can never stop. It always keeps on going. So whatever you have in business always keeps on going. It's the independent variable. It never changes. I want to know, with this information, number of males in 2030. How would you find this information? You have the bar charts, you have the values, you know the time. I want to know, you can make future predictions of this by looking at what happened in the past. How do we do that? Well, first off, find the rate of change of the number of males from the beginning to the last piece of information we have. Find the rate of change. When I say rate of change, what's the word of that in mathematics? Whenever you hear the words rate of change, that means slope. Okay, so let's go back. What is the formula for a slope? Let's try to remember that back all the way back in algebra. What's that? That's the equation. That's the linear equation that we're trying to get to. The slope is the m. In words, how would you define slope? Very good. Rise over run. Let's look at this thing. We have two dots. this is my x, these are my x values, and these are my y values. Oop, y2. The rise, the vertical change, how far does it go up or down versus how far does it go over? So the question is, how do we find how far it moves up and down? With these informations. To find the difference between two numbers, what do I do? Like, how far is it between 3 and 9? How far is it from 11 to 48? How about from 20 to 95? $75. So how do I get these numbers? With these two numbers, how do I get these numbers? Nope. 9 minus 3 equals 6. 48 minus 11 equals 37. 95 minus 20 equals 75. So if this is my first x and this is my second x, the difference would be x2 minus x1. So it's always the second number minus the first number. And likewise here, it's the second number minus the first number. I want to know how far is it from there to there. And likewise there. So, vertically, I'm looking at y2 minus y1, and horizontally, it's x2 minus x1. There's the formula. But what do these numbers mean? What does x1, x2, y1, y2, what does that mean? What do they refer to? Well, remember, the horizontal are the years. This is the time. Right here. We have, this is x1, this is x2. Number 200 is y1. 270 is y2. So how far it goes up, that's my y values. The years are my x values. So I have, in my first year, at the year 2000, it's 200. And then at the year 2020, it's 270. Let's make it 280, I think easier for us. So this is x1, y1, x2, y2. So find the slope, find the rate of change. What is y2? 280. What is y1? 200. x2, 2020. And x1 is 2000. 280 minus 200 is 80. 2020 minus 2000 is 20. The zeros cancel. 8 divided by 2 is 4. So what this tells us is each year we get 4 new employees a year. 4 new male employees a year. That's what it tells us. That's the rate of change. So we know our slope is 4. We know our beginning number was 200. And we want it at 2030, or 30 years down the road. We wanted to be, since we started at 2000, we want to know how it's going to be there. And we gain 4 people a year. So y equals mx plus b, 4 times 30 plus 200. 120 plus 200 is 320. We're going to have 320 males on the year 2030. That's what's projected, estimated. So these represent, this is year 1, the year 2, the amount of people there. I need to know that because, as you said, this is the formula we need to have to future references. That's how you use bar charts. And we also have line charts, line graphs. So this is the year 2000, 2010, 2020, 2030, 2040. 10,000, 20,000, 30,000, 40,000, 50,000. You plot the points. You have the time and the amount of data you're looking for, and connect the dots. And what years, now from this you can tell me a bunch of stuff. What years or when were we above 35,000 employees? So 35 would be here, so draw. So it's about when? 2028 or 2027. So again, it's an estimate. We have no growth. Since it's a flat line between 2030 and since it's a flat line here, we had no growth between 2030, 2040. When did we lose the most employees? Well, the only one's going down is this one. We lost the most employees between these 2 years, or decades. So that's how you use a bar chart. I mean a line chart. That pretty much covers that first 2 sections. What do y'all think? I do apologize. I hate to say it. Chapter 1 has never been my favorite chapter because it's boring. It's very boring to me too. No, it gets more interesting when we get to chapter 2, 3, and 4 because then we start dealing with actually logic stuff, the truth tables, and actual statements. We get to now prove what is a counterexample, what is a inverse, what is a converse. All right, so what's today? Tuesday? Try to do your chapter 1 stuff, and we'll see how far you get. By next time, yeah. Yeah, by Thursday. And what we do on Thursday is we'll finish up the chapter and on my math lab. Do your work on my math lab.
You know what for me, it's the first time never, I love math, but I never really